Okay, let's take a look at 3.5. We're going to look at tree and Venn diagrams. A tree diagram is going to be a diagram that's going to help us visualize probabilities so that we don't have to use as many formulas when we're doing them. So we have in an urn, there are, we could say, just a bowl or anything that we're putting these in. So we have 11 total balls. There are 3 red balls, and there are 8 blue balls. Okay, so we could do R1, R2, R3, and then B1 through 8. Okay, we're going to draw 2 balls at a time with replacement. So replacement means I'm going to put the first ball back in the urn. So every time I am drawing, that means that I am going to have 11 balls to draw from. Okay, so each time I do a drawing, there's 11 chance. Okay, 11 chances of getting either red or blue. Okay, so 3 chances of red and 8 chances of blue. So my first draw, I could get 8 chances of blue, 3 chances of red. Let's say I get a blue on the first draw, then I put the blue back in the urn. Okay, then I'm going to draw again, and I have 8 chances of getting a blue ball again. I also have 3 chances of getting a red ball. Okay, so to find those probabilities, I'm going to go like this. I'm going to go, I have 8 chances of getting a blue on the first draw times 8 chances of getting a blue on the second draw. So 64 chances of getting a blue. I could also do 8 chances of getting blue on the first draw, 3 chances of getting red on the second draw. So that would be an 8 times 3. So that would be 24 for getting blue and then red. Okay, now let's say I get red on the first draw. I have 3 chances of doing that, and then on the second draw I have 8 chances of getting blue. So red-blue would be 3 times 8, 24. And then I could get red and then red, which would be 3 times 3, 9. Okay, so I have these different ways that I could get these outcomes. Now, if I add all of these together, that is going to give me, let's see here, $121. Okay, so there's 121 different ways that I could draw these balls, because you could have B1, B2, B3, all the way through 8, or red 1, red 2, red 3, all the way through 8. Okay, so that's going to be the size of my sample space. There is an easier way to do the calculation for sample space, though. That is going to be the number of possible outcomes raised to the number of experiments. Okay, so here I have 11 possible outcomes because there's 11 balls. So 11, and I am doing this twice, 11 squared is also 121. So you could do that, and this is when we are doing replacement. Okay, so with replacement, we are going to multiply by the number of experiments. If we are not replacing, then we're just going to multiply, which we'll look at in the next example. So let's do some probabilities. So we have 121 total different ways that this could happen. What is the probability of getting red and then red? Well, if I look at the tree diagram, I can get that easily. Red, red, right here, there's 9 ways to do that out of a total of 121. So there I would do 9 divided by 121. And that would give me 0.074. Okay, B is the probability of red, red, or blue, red. Or I'm going to add. So let's see. Red, red, there's 9 ways of doing that. Or I could do blue, red. There's 24 ways of doing that. So that's going to give me 33 out of 121, which is going to give me a 0.273. Okay, next possibility is red on the first draw and B on the second draw. Okay, now that's an and probability, which could use multiplication, but we don't need it because we already have that right there. Red, then blue. So that's 24 out of 121. And that's going to give us 0.198. Okay, and then part D, you have R on the second draw given B on the first draw. Okay, so now this does, with given, that restricts our denominator to only B on the first draw. So if I look at my tree diagram, I could get blue on the first draw here, so 64. And I could get blue on the first draw here, so 24. So my denominator here is going to be 88. Okay, so 64 or 24, because blue on the first draw, either blue-blue or blue-red. Now within that sample space, red on the second draw. Well, that's right here, blue-red. So there's 24 ways to do that out of 88, which is going to give us 0.273. Okay, then E, you have probability of blue, then blue. So I look up here, blue, blue, 64 out of 121. So 0.529. And then F, you have P, blue on the second draw, given red on the first draw. Okay, so our sample space now is red on the first draw, so that's going to be these guys here. Red on the first draw. So that sample space is going to be 24 plus 9, 33. Red on the second draw, this is red on the first, this is red on the second, so there's 9 of those. 9 out of 33. Let's see here. Oh, sorry, it's blue on the second draw, not red on the second draw. Just kidding. I was reading that wrong. So blue on the second draw, that would be the 24 out of 33. Red on the first draw would be 9 out of 33, and then red on the second draw, given red on the first, would be 9 out of 33. Blue on the second draw, given red on the first, 24 out of 33, which is 0.727. Okay, let's look at another example. So we have a litter of kittens is available for adoption at the Humane Society. They have 4 tabby kittens and 5, I think that's supposed to be brown, sorry. 5 brown. Okay, a family comes in and randomly selects 2 kittens without replacement for adoption because I'm going to pick a cat. I'm not going to pick the same cat twice because I want 2 cats. Okay, so this is a without replacement. So slightly different here. Okay, so you could get an orange cat and then an orange cat. You could do orange and then brown. You could do brown and then orange, or you could do brown and then brown for our cats. Okay, there are 4 orange cats and there are 5 brown cats. Okay, so here for orange cats, you would have 4 out of 9. So 4 out of 9 orange cats. But then on the second draw, there's only 3 orange cats left. And there's only 8 total cats left because we already got an orange cat and there's 1 less cat in the litter. So we would do 4 times 3. There's 12 ways that I could get orange and then orange. Okay, with my different cats. Okay, you could get orange and then brown. Okay, we have to cross all these out, sorry. Okay, so orange and then brown. So after I pick the orange cat, there's only 8 cats left, but there's still 5 that are brown left. So 4 times 5 here is going to be 20. Okay, so 4 times 3, 4 times 5, 20. Brown, so there's 5 out of 9 brown cats. Okay, let's say we get a brown on the first. Okay, then there's 4 orange cats left. There's only 8 cats total left, though. Okay, so that's going to be 5 times 8, 40. All right, brown and then brown. There's 5 brown cats. Well, I already got a brown cat, so now there's only 4 brown cats left, and there's only 8 cats left total. So 5 times 4, 20 ways to get brown, brown. Now if I add all of these together, let's see, 12 plus 20 is 32, plus 40 is 72, plus 20 is 92. That's not going to be our sample space there because we want to look at how many, because we're replacing. So if this was with replacement, that would be the sample space. But in this case, for the sample space, because there's no replacement, okay, what we're going to do here is you have 9 cats, you're going to pick one, then you're going to have 8 cats. So that sample space is going to be 72, 9 times 8. Okay, so with replacement, you're just going to do the permutation of that. So the factorial, almost the factorial, of that 9 times 8. Let's say we're doing 3 cats, it would be 9 times 8 times 7. All right, let's do some probabilities. So what is the probability that both kittens are orange? Okay, well, that would be orange, orange. So orange, orange would be 12 out of 72. Let's see what that gives us. Do a different one here. 12 divided by 72, 0.167. What is the probability that one of each coloring is selected? Okay, so that is OR, so probability of orange brown or brown orange. So orange brown or brown orange. Okay, so that's 20 plus 40 over 72. So 60 over 72. So that's going to be 0.833. That, yeah, 0.833. Okay, I just saw my mistake here. When I'm looking at my sample space here, I did 5 times 8 instead of 5 times 4 when I was doing this. So I pulled the 40 down when that should actually be a 20. So let's go ahead and fix that. All right, so 5 times 4 is 20, which then this would actually add up to 72 for our sample space. So we could add these together, 72 over 72, or do the 9 times 8. But going back to this problem here, this would be 20 plus 20, not 20 plus 40. So I noticed that mistake there, I just carried that wrong number down, carried it through the whole problem. We all kind of do that sometimes. But it is important to double check the work and make sure that we don't do stuff like that. So that's what I was doing there. So 40 out of 72 would give us 0.556. All right, next one is C. So what is the probability that the second kitten is orange? Okay, given that the brown kitten was chosen first. Okay, so the probability, so the sample space here for brown first is going to be these guys here, 20 plus 20. So brown first, so that would be 40 for that sample space. Now inside that sample space, because now I'm only looking here, the probability that the second one is orange is this one right here, so 20 out of 40. So 1/2, 0.5 there. And then D, what is the probability of choosing 2 kittens of the same color? So that would be orange, orange, or brown, brown. So we're adding. So orange, orange is 12 out of 72. And brown, brown is 20 out of 72. So 12 plus 20 is 32 out of 72. And that is going to be 0.444. Okay, so that's tree diagrams. Venn diagrams, hopefully you've seen them before, fairly simple. Helps you visualize different outcomes in a sample space. So let's take a look at this Venn diagram here. It's usually a box with circles in them. The overlapping part of the circle is what the two circles would have in common. So this middle part right here, the overlapping circles is what A and B would have in common to them. All right, so suppose an experiment has outcomes: black, white, red, orange, yellow, green, this is cutting off blue, green, blue, and purple. Okay, black, white, red, orange, yellow. Okay, where each outcome has an equal chance of occurring. A is green, blue, and purple. B is red, yellow, and blue. Okay, so we want to construct the Venn diagram. The first thing we do is we look for what they have in common. So when I look at A and B, they both have blue. Okay, so I'm going to put the blue right here where they overlap. Now, A has green and purple and B does not, so I'm going to write that over here where it's in the A circle, but it's not overlapping. And same thing with B. Red and yellow are in B, but they don't overlap into the A circle. And then I'm going to look back up here at all of my possible outcomes. And I'm going to cross out what I've already written down. So I already wrote down green, purple, blue, red, and yellow. I did not have black, white, or orange. Those are still possible outcomes, so those are still in this S, your sample space. So we're going to write those down out here. Okay, so black, white, and orange. Okay, so now your Venn diagram is filled out. Okay, possible outcomes, including everything in our sample space. So A and B are written. Now you want A union B. Remember, that's both, everything to A and B. So we would just write all of those out. So you have green, purple, blue, red, and yellow. A intersect B is that blue right there, what they have in common. And then A union B complement is what is not in the circles. So that's this black, white, and orange. So it's really easy to do these questions here once this is drawn out, because you can see where everything is. So just one more example of that. Okay, we're flipping two coins. A is tails on the first coin, B is tails on the second coin. Construct a Venn diagram that shows this. So let's first do the sample space of what could happen. Okay, so we could do that with a Venn diagram, a tree diagram. So you could have your first draw, you could get heads or tails. And then the second flip, heads or tails again. Either way. So that gives us our possible outcomes. Heads, then heads. Heads, then tails. Tails, then heads. Tails, then tails. All right, well, A is tails on the first coin. All right, so tails on the first coin, here and here. So tails, heads, or tails, tails. B, tails on the second coin. That's here, heads, tails, or here, tails, tails. So if I construct my Venn diagram, they both have tails, tails in common, so that would go in the middle. A has tails, heads, and B has heads, tails. I have not accounted for heads, heads. So that's going to go in my sample space. Okay, so I have set A and B. A union B would be all of these. So tails, heads, tails, tails, heads, tails. A intersect B is just tails, tails. A intersect B complement. That's intersect B complement. That's everything but tails, tails. So that's heads, heads, tails, heads, or heads, tails. It's everything but this. But if I had a union B complement, that's everything but what's in the circle, so that's just heads, heads.